For this question, we start off receiving $5 per year, and then it keep increases until it reaches 100, and then the payment remains at 100 forever. And then at this interest rate, we need to find the present value. So first, this seems really easy. So let's just, again, draw a timeline. So we start at $5 and then 10, so it keeps increasing until it reaches 100. And then if you do a bit of division, 100 divided by 5 is equal to 20, so you know that this process takes 20 years for it to reach from 5 to 100. And then once it reaches this point, all subsequent payments are going to remain at 100 all the way to infinity. So the present value of this, you can actually break it up into two parts. So we have increasing the annuity of 20 years, so it's this part over here. And then this subsequent section, this is a perpetuity of $100. So 100 divided by I. And then this expression gives us the present value at time 20, so we just need to take it back to time 0. So we multiply by v to the power of 20. And then if you just substitute your numbers in, you'll find that this is equal to 785.40. So essentially you can say you're done. So this is one way of doing it, and this seems fairly simple. So once again, I'm going to introduce a different way of thinking about things. So first of all, let me just solve for this kind of situation in the general case. And then I will derive a new formula for you to calculate situations like this. So let's say I start at time 1 all the way to time n. And then the payments increase by x. So 2x all the way to nx. And then each subsequent payment is going to remain at nx. So we do the exact same thing as we did before. The present value is equal to this increasing annuity of n years. And then this part, we have v to the power of n times nx over I. So this is the perpetuity section. So bring it back to time n, and then we bring it back to time 0, so with the v to the power of n. And then in order to derive a formula for this type of situation, I'm going to use the increasing annuity formula. And then if you add these together, you find that there's a minus nxvn, and there's also another nxvn, so both of these they cancel out. So in the end you get x times ani. So this is a much simpler formula than this whole thing over here, right? So you can actually try applying this formula to this situation here, and you will get the same result. And then you can actually provide what we just did was an algebraic proof, but you can actually provide a verbal interpretation of this expression over here. So let's just write down what our expression was. And then notice how we can actually break it up like this. An annuity due and x over I. So what this tells us is that all these payments, it's equivalent to receiving x over I for n years, all the way to n minus 1. So this is an annuity due that pays x over I per year. And then don't forget, if you draw it out in a timeline, it looks something like this. And then don't forget x over I. So what exactly is x over I? X over I is just a perpetuity of x, right? So I'm just going to open a new page. So x over I is a perpetuity that pays x every year, all the way to infinity. And so if we're receiving x over I at time 0, at time 1, all the way to time n plus n minus 1, this essentially is the same thing as receiving x dollars, all the way to infinity. So this x over I, this is a perpetuity that starts at time 1 all the way to infinity. This x over I is another perpetuity that starts at time 1. So the first payment, so this is the present value at time 1. The first payment starts at time 2. So again, x, and all the way x, and all the way to infinity. And then this third payment is the same thing, so you get another x divided by I at time 2. First payment is at time 3, so you get time 3, so you get another x, so it keeps on going all the way to infinity. And in this process, this x, you see that this looks kind of like a ladder. and then it keeps going up all the way till n minus 1. So it keeps going all the way till here. So x all the way, and keeps on going to infinity. And then this only stops at time n. So after time n, it stabilizes so that this ladder does not go up anymore. So from this expression, you see that this expression is equivalent to a payment that looks something like this. And then if you add all these payments up, you see that the first year is a payment of x, second year is a payment of 2x, third year is a payment of 3x, all the way when you add to n minus 1 is a payment of n minus 1x, and then at time n it's a payment of nx. And then because the ladder is not going to go up again after n, so remember that all these terms stop at n minus 1, there are no more terms after n minus 1. So all the subsequent x's, when you add them together, it's just nx. So you see that this payment stream over here is actually identical to our original case. So actually by a verbal argument, so recall that we arrived at this diagram here through this expression. We interpreted this expression by breaking it up into an annuity due of perpetuities. And then we broke it up, and then we found that this actually leads to an expression that is the same as this. So by arguing through these diagrams, we can actually prove that this formula here is the same as this without doing any of the algebra in between. So this is just another way of thinking of things. So I hope that through these examples you can see that there are many different ways of breaking up a problem, and then you can, by attempting more of these kind of experiments yourself, you'll gain a better understanding of what's going on.